Something absolutely extraordinary has just been photographed in our solar system. And I have to tell you, as a physicist who spent decades studying the cosmos, what we're witnessing right now is making some of the brightest minds in astronomy ask a question we never thought we'd seriously consider. Could this object be something other than entirely natural? On November 9th, 2025, two astronomers captured an image that has sent shockwaves through the scientific community using telescopes over just a 15-minute window. Frank Nebling and Michael Yeager photographed the interstellar object known as 3I Atlas. What they saw defies everything we thought we understood about comets. The image reveals massive jet structures extending from this mysterious visitor. Not one jet, not two, but three distinct jets shooting out into space. Two anti-tail jets pointing directly toward the sun, stretching nearly 1 million kilometers into space. That's roughly 3 times the distance from the Earth to the Moon. But here's where it gets truly bizarre. There's a third jet, a collimated beam shooting away from the sun, extending an incredible 2.85 million kilometers. That's about 7 times the distance from Earth to the Moon. Think about that for a moment. We're talking about structures that dwarf anything we've ever seen from a typical comet. The scale alone is staggering. Now, I need you to understand just how remarkable these measurements are. This is 3 orders of magnitude larger than what we typically observe. That's 1,000 times larger than the glowing halo around 3I Atlas that the Hubble Space Telescope photographed back in July of this year. But size isn't the only thing that has scientists scratching their heads. These jets are behaving in ways that fundamentally challenge our understanding of how comets should work. Let me explain the physics here. When a comet approaches the sun, ice on its surface sublimates. That means it turns directly from solid to gas without becoming liquid first. This process creates jets of material that typically flow at speeds of about 0.4 kilometers per second. That's roughly the speed of sound in gas at this distance from the sun. It's a relatively gentle process, powered purely by sunlight heating frozen volatiles. Now here's the problem. For these jets to extend as far as they do, they would need to have been continuously ejecting material for months. The tail jet would require at least 3 months of constant outflow. The anti-tail jets would need at least 1 month of sustained activity. That's a tremendous amount of material being expelled. But it gets stranger. Harvard professor Avi Loeb, one of the leading voices analyzing this object, calculated something remarkable. For these anti-tail jets to extend nearly 1 million kilometers against the solar wind, they must have incredible density and pressure. The solar wind normally blows at 400 kilometers per second. That's 1,000 times faster than typical comet outflow. Yet somehow, these jets are pushing against that wind and winning. The mathematics reveals something shocking. The mass loss rate required to maintain these structures is approximately 50 billion tons per month. Let that sink in for a moment. 50 billion tons every single month. That's comparable to the minimum estimated mass of the entire object itself. So we have an object losing mass at a rate that seems almost impossible for a natural comet. We have jet structures on a scale never before witnessed, and we have an object that, based on these mass loss calculations, would need to be at least 10 kilometers in diameter just to survive this kind of activity. But here's where things take an unexpected turn, and this is what's really captured my attention as a physicist. 3I Atlas showed virtually no signs of activity for months before its closest approach to the sun. On October 30th, astronomers were tracking it since July, and it appeared relatively quiet. No significant non-gravitational acceleration, no massive outbursts, nothing to suggest it was about to put on this kind of show. Then it swung around the sun at perihelion, its closest approach, and suddenly everything changed. Multiple jets appeared seemingly out of nowhere. the behavior shifted dramatically. It's as if someone flipped a switch. Now, some scientists are proposing that pockets of volatile ices buried beneath the surface suddenly became exposed to intense solar radiation. During perihelion, the heat triggered a massive outburst, creating these enormous jets. It's a plausible explanation. Comets can be unpredictable, and we've seen outbursts before. But others, including Professor Loeb, are asking a different question. What if these aren't jets caused by sublimating ice at all? What if we're looking at something else entirely? Consider this from a purely physics perspective. If instead of natural sublimation, these jets were produced by some form of propulsion system, the mass requirements drop dramatically. Chemical rockets, the kind we use here on Earth, produce exhaust velocities of 3 to 5 kilometers per second. That's 10 times faster than comet sublimation ion thrusters. Even more advanced technology reach exhaust speeds of 10 to 50 kilometers per second. With those kinds of speeds, the required mass loss could be 1 to 2 orders of magnitude lower, maybe even less than 1% of the object's total mass would be needed as fuel. Suddenly, the impossible becomes possible. Now, I'm not saying 3I/ATLAS is a spacecraft, but I am saying that the data is forcing us to ask questions we never thought we'd have to ask about an interstellar visitor. The numbers don't quite add up for a conventional comet explanation. And when the numbers don't add up in physics, we have a responsibility to explore alternative hypotheses, no matter how unconventional they might seem. This is the third interstellar object we've confirmed passing through our solar system. The first was Oumuamua in 2017, which displayed its own set of bizarre characteristics. The second was Comet 2I/Borisov in 2019, which behaved much more like a typical comet. And now we have which is in a category all its own. What makes this moment so exciting is that we're watching this unfold in real time. Telescopes around the world are now pointing at as it moves away from the sun. Its angular separation from the sun just crossed 30 degrees, meaning Earth-based observatories can finally observe it again without the sun's glare interfering. Over the coming weeks, astronomers will be measuring the composition of these jets, their velocity, their density, and searching for any fragments that might have broken off during perihelion. These observations will help us determine whether we're witnessing an extraordinary natural phenomenon or something that challenges our assumptions about what's possible in the universe. The images from November 9th are just the beginning. They're a preview of what's to come. We're living in a remarkable time. For the first time in human history, we have the technology to study objects from other star systems in detail. We can analyze their composition, track their trajectories, and search for clues about the environments they came from. Every piece of data we gather brings us one step closer to understanding our place in the cosmos. 3I Atlas is currently about 326 million kilometers from Earth. That might seem impossibly far, but in astronomical terms, it's practically in our backyard, and it's getting closer. On December 19th, it will make its nearest approach to Earth at 269 million kilometers. That's about 100 times larger than the extent of its jet structures. So we won't be in any danger, but it will give us our best opportunity yet to study this enigmatic visitor up close. Now let's talk about what happened during those critical hours when 3I Atlas made its closest approach to the sun, because this is where the story gets truly strange. October 29th and 30th, 2025. These dates are now etched in the minds of astronomers studying this object. 3I/ATLAS reached perihelion, swooping to within 203 million kilometers of our star. For context, that's just inside the orbit of Mars. For an interstellar visitor, this was its moment of maximum solar heating, maximum stress, and apparently maximum activity. What happened next has sparked intense debate in the astronomical community. In the days following perihelion, observers began reporting something unexpected, not just the three massive jets we discussed earlier, but a total of seven distinct jet structures emanating from three Atlas. Seven separate streams of material, each pointing in different directions, creating a complex firework display in space. Now, multiple jets aren't entirely unusual for comets. We've seen comets with several active regions on their surfaces, each producing its own jet as different areas become exposed to sunlight. But the configuration, the intensity, and the timing of these seven jets are raising eyebrows. Professor Avi Loeb has been following this closely, and he's asking a question that makes some traditional comet scientists uncomfortable. Did 3I Atlas just break up near the Sun? Here's why this matters from a physics standpoint. When a comet breaks apart, we typically see distinct fragments, each with its own trajectory. We see a debris field. We see brightness changes as the fragmentation exposes fresh ice to sunlight. It's a dramatic, observable event. But here's the puzzle. While we're seeing these seven jets, we're not seeing clear evidence of multiple fragments moving on separate paths. The observations show jet structures, streams of material being ejected, but the core object appears to still be intact, or at least mostly intact. This creates a fascinating scenario. Either 3I Atlas experienced a partial fragmentation where pieces broke off, but the main body survived, or something else is causing these multiple jets to appear simultaneously. Let's consider the fragmentation hypothesis first. Comets are fragile objects. They're often described as dirty snowballs, mixtures of ice, dust, and rock, loosely held together by their own weak gravity. When a comet gets too close to the Sun, thermal stress can literally tear it apart. We've witnessed this before with other comets. The most famous case is probably Comet Shoemaker-Levy 9, which broke into multiple pieces before crashing into Jupiter in 1994. We've also seen comets fragment as they round the Sun, creating spectacular but short-lived displays before they vanish completely. 3I Atlas fragmented, even partially, it would explain the sudden appearance of multiple jets. Each fragment, or each newly exposed surface, could be producing its own outgassing stream. The intense solar heating at perihelion would trigger rapid sublimation of ice that had been buried and protected for potentially billions of years. But there's a problem with this explanation. The energy and duration of these jets seem inconsistent with simple fragmentation. Remember, we calculated that maintaining these structures requires massive sustained outflow over weeks or months. Fragmentation events are usually much more explosive and short-lived. This brings us to alternative explanations that are, let's say, less conventional. And as a scientist, I think it's important we discuss these openly. What if these seven jets aren't the result of passive sublimation or fragmentation? What if they represent active processes? Now, before you dismiss this as science fiction, consider that we're already comfortable with the idea of active geology on other worlds. We know that moons like Enceladus and Europa have geysers powered by internal heat. We know that geological activity can persist for billions of years. But 3I Atlas isn't orbiting a giant planet that could provide tidal heating. It's an interstellar object traveling alone through the void. So where would the energy come from? This is where the conversation gets really interesting from a physics perspective. If you were to design a propulsion system for an interstellar journey, you'd want it to be efficient, long-lasting, and you'd want to conserve your fuel until you really needed it. You'd coast through the empty void of interstellar space, perhaps for millions of years, using minimal energy. And then, when you encountered a star system, when you had access to abundant solar energy, or when you needed to make course corrections, that's when you'd activate your systems. Now, I want to be absolutely clear. We have no direct evidence 3i Atlas is anything other than a natural object. But what we do have is a pattern of observations that doesn't quite fit the standard comet model. And in science, when observations don't match predictions, we have two choices. Either refine our models of how natural comets work, or consider that we might be looking at something outside our existing categories. The timing is particularly intriguing. 3. iAtlas showed minimal activity for months. Astronomers tracking it from July through September saw a relatively quiet object. Then perihelion happens, and suddenly, boom, 7 jets, massive outflow, dramatic changes in behavior. One explanation is that the object has a very low thermal conductivity. Heat from the sun takes time to penetrate into the interior. So even though the surface was being heated for months, the real fireworks didn't start until the heat finally reached deeper layers of volatile ices. Once those ices started sublimating, the pressure built up and multiple weak points on the surface gave way simultaneously, creating the multi-jet structure we're observing. That's a perfectly reasonable natural explanation. It requires a specific internal structure and composition, but it's within the realm of known cometary behavior. But let's play devil's advocate for a moment. If you were piloting an interstellar craft and you needed to perform a maneuver, when would you do it? You'd do it at perihelion, when you're moving fastest, when you have the most solar energy available, and when any course correction has the maximum effect on your trajectory. It's basic orbital mechanics. A small change at perihelion translates to a large change in your final trajectory. The 7 jets could represent vectored thrust, different nozzles firing to achieve a specific change in velocity or direction. The fact that they're pointing in multiple directions could indicate a complex maneuver rather than random outgassing. Again, I'm not claiming this is what's happening. I'm pointing out that the observations permit multiple interpretations, and we shouldn't close our minds to possibilities just because they seem unlikely or uncomfortable. Now, here's where things get frustrating, and I have to say, as someone who's worked in science for decades, this is deeply disappointing. On October 2nd and 3rd, 2025, 3i Atlas passed within 29 million kilometers of Mars. The Mars Reconnaissance Orbiter's high-rise camera photographed it from the side with 30 km per pixel resolution. While Earth-based telescopes see the comet head-on, high-rise captured a profile view that could reveal the nuclear structure, jet distribution, and potential fragments. This data was captured 40 days ago. It still hasn't been released. Why? On October 1st, the United States government entered a shutdown. NASA has been paralyzed for 6 weeks. Most NASA employees have been home without pay, unable to do their jobs. The agency has lost 20 to 25% of its workforce this year through early retirements and buyouts. Key positions are filled by interim directors. Meanwhile, commercial space companies are cherry-picking NASA's best engineers. Professor Avi Loeb requested release of the high-rise images. Congresswoman Anna Paulina Luna publicly supported this, saying scientific data shouldn't be held hostage by politics. The space community is asking, where are the images? This isn't classified intelligence. These are images of a comet passing through our solar system. The data belongs to humanity. The 40-day delay has cost valuable time. These images were taken just before perihelion, capturing the object before the dramatic outburst and 7 jets appeared. Comparing pre- and post-perihelion observations could be crucial for understanding what happened. NASA's Juno spacecraft will observe 3i Atlas in March 2026 from 53 million kilometers. The European Space Agency's JUICE spacecraft is currently 64 million kilometers away. but both are too far to intercept the jet structures or directly sample material. The high-rise images are our best opportunity for detailed structural information. When political dysfunction interferes with scientific progress, we all lose. The space community is calling for immediate release while 3I atlases still observable. Now, let's talk about probability, because when you look at the numbers surrounding 3I/ATLAS, things start to get really strange. And by strange, I mean statistically improbable, to the point where it challenges our assumptions about what we're really looking at. Professor Avi Loeb has done some fascinating calculations about just how unlikely this object is, and the results are frankly astonishing. First, let's consider the mass of 3I/ATLAS. Based on the observations we've discussed, the calculations of material being ejected, and the sustained nature of the jets, this object must have a mass of at least 33 billion tons. That's assuming it's a solid body with a density of about half a gram per cubic centimeter, which is typical for comets. This means 3I atlases a diameter of at least 5 kilometers, possibly 10 kilometers or larger, if most of its nucleus survived perihelion. Now let's compare that to Oumuamua, the first confirmed interstellar object discovered in 2017. Oumuamua was tiny. Based on observations, its mass was estimated at roughly 30 million tons, maybe less. Do the mathematics. 3I atlases at least 1,000,000 times more massive than Oumuamua, 1,000,000 times. Here's the problem. If interstellar objects arrive randomly from the galactic neighborhood, we'd expect to see a distribution of sizes, lots of small objects, fewer medium ones, and very rare large ones. It's a pattern we see throughout nature. There are more pebbles than boulders, more asteroids than planets, more small comets than giant ones. Given that we've only confirmed 3 interstellar objects passing through our solar system in recorded history, what are the odds that the third one would be 1,000,000 times more massive than the first? Professor Loeb calculated the probability. If all rocky material in interstellar space is packaged in large bodies, the size of 3I atlas or smaller, the likelihood of seeing such a massive object so soon in our survey period is less than 0.1%, 1 in 1,000. But it gets worse. If there's an equal amount of total mass distributed across all possible object sizes, meaning you're just as likely to encounter small objects as large ones in terms of total material, the probability drops to 0.00005%. That's 1 in 200,000. These are not good odds. We would expect an object with a diameter above 10 kilometers to be delivered to our vicinity, maybe once per 10,000 years or longer. Yet here we are, less than a decade into actively searching for interstellar objects, and we found one. But wait, there's more. The statistical anomalies don't stop with size. 3I atlases a retrograde orbit. That means it's traveling in the opposite direction to the planets in our solar system. It's going against the flow, so to speak. That's not particularly unusual for interstellar objects. They can come from any direction because they're not bound by the sun's gravity. But here's what is unusual. The orbital plane of 3I atlases aligned with the ecliptic plane, the flat disk in which Earth and the other planets orbit the sun, to within 5 degrees, 5 degrees. Out of all possible angles it could have approached from, it happens to be almost perfectly aligned with our solar system's plane. The probability of a random interstellar object arriving on a retrograde trajectory that's aligned within 5 degrees of the ecliptic, 0.2%, 1 in 500. Now here's where it gets really interesting from a statistical standpoint. These probabilities aren't independent, they multiply. If 3I atlas is truly a natural object arriving randomly from interstellar space, we need to account for both anomalies. the extreme mass compared to previous discoveries, and the aligned retrograde orbit. Multiply 0.1% by 0.2%, and you get a combined probability of 0.02%. But if we use the more conservative estimate that accounts for the full mass distribution, we get 0.00001%. That's 1 in 100 million. Let me repeat that. If 3I Atlas is a natural comet that arrived randomly from interstellar space, the odds of it having the mass and orbital characteristics we observe are approximately 1 in 100 million. Now, I want to be clear about what this means and what it doesn't mean. Low probability events happen all the time. Someone wins the lottery despite incredibly long odds. Rare diseases affect people. Lightning strikes in unexpected places. The universe is full of unlikely occurrences. But when you're doing science, low probability outcomes should make you pause and reconsider your assumptions. They should prompt you to ask whether there might be alternative explanations that better fit the observations. If I told you I won the lottery once, you might congratulate me on my luck. If I told you I won the lottery 3 times in a row, you might start to wonder if something else is going on. Are the drawings rigged? Did I find a flaw in the system? Is there information I'm not sharing? That's essentially where we are with 3I/ATLAS. We have an object that, if natural, represents an extraordinarily unlikely combination of characteristics, and that should make us ask questions. One possibility is that we're simply unlucky or lucky, depending on your perspective. Maybe we just happen to live at a time when a giant interstellar comet passes through our solar system on an unusual trajectory. It's improbable, but not impossible. The universe is vast, and given enough time and enough star systems, even 1 in 100 million events will occur somewhere, sometime. Another possibility is that our models are wrong. Maybe interstellar space contains far more large objects than we currently estimate. Maybe the mass distribution of comets in other star systems is different from what we observe in our own solar system. Maybe there are formation or ejection mechanisms that preferentially produce large interstellar wanderers. If that's the case, then finding 3I Atlas isn't as unlikely as the calculations suggest. We're learning that our assumptions about interstellar material need to be revised. That would be valuable scientific knowledge. But there's a third possibility that we need to consider, even if it makes some people uncomfortable. What if 3I Atlas isn't a random arrival? What if its trajectory and characteristics aren't the result of chance? If you were planning an interstellar mission, how would you design your trajectory? You'd probably want to pass through the plane where planets are most likely to be found. You'd want to maximize your chances of a close encounter with interesting objects. An aligned trajectory isn't random in that context. It's strategic. And if you're bringing a substantial craft with fuel reserves and possibly equipment for course corrections, you'd naturally be much larger than a small natural object tumbling through space. I'm not saying 3I Atlas is artificial, but I am saying that the statistical improbabilities we're observing would be less improbable if the object's characteristics resulted from design rather than chance. This is a testable hypothesis. If 3I Atlas is natural, we should eventually discover more large interstellar objects. The statistics should balance out over time. We should find evidence that our models of interstellar material distribution need updating. If it's something else, we might continue to see anomalies that can't be easily explained by natural processes. We might detect patterns in the behavior that suggest intentionality rather than randomness. There's also the question of Oumuamua. Remember, the first interstellar object also displayed unusual characteristics. It had a non-gravitational acceleration that couldn't be explained by typical cometary outgassing. Because no gas or dust was detected around it, its shape was unusual, either extremely elongated or very flat, unlike any comet or asteroid we'd seen before. It tumbled in a peculiar way. Some scientists called it a dark comet, a comet without visible comet activity, but that's essentially an admission that it didn't behave like natural comets do. We're inventing new categories to accommodate observations that don't fit our expectations. If you have 2 out of 3 confirmed interstellar objects displaying characteristics that challenge natural explanations, at what point do you seriously consider that maybe, just maybe, not everything entering our solar system is purely natural in origin? Now, before anyone accuses me of promoting conspiracy theories, let me be absolutely clear. I'm not claiming aliens. I'm not claiming UFOs. I'm doing what scientists are supposed to do, which is following the data wherever it leads and considering all reasonable hypotheses that fit the observations. The hypothesis that some interstellar objects might be technological artifacts is not inherently unreasonable. We've sent our own probes into interstellar space. Voyager 1 and 2 are currently leaving our solar system. They'll drift through the galaxy for millions or billions of years. If another civilization encounters them, they'll recognize them as artificial. Given that there are billions of Earth-Sun analogues in our Milky Way galaxy, most of which are billions of years older than our solar system, and given that it would take less than 1 billion years for a spacecraft to cross the galactic disk, even at relatively slow speeds, the existence of artificial interstellar objects is not only plausible but arguably expected. The question isn't whether such objects could exist. The question is whether we're observing one, and to answer that question, we need more data. We need spectroscopy of the jets to determine their composition. We need precise trajectory tracking to detect any non-gravitational accelerations. We need those high-rise images from Mars to see the object's structure. We need follow-up observations. As 3I Atlas continues its journey, what we don't need is premature dismissal based on assumptions rather than evidence. For too long, the search for extraterrestrial intelligence has been confined to radio telescopes scanning for signals. We've been looking for messages. But what if the first evidence of extraterrestrial technology isn't a message? What if it's an object passing through our solar system, displaying characteristics that don't quite match natural explanations? This is why the statistical improbabilities matter. They're not proof of anything, but they're a red flag that demands serious investigation rather than reflexive skepticism. Professor Loeb recently made a bet with Michael Shermer, executive director of the Skeptics Society. The bet is that within 5 years, by December 31st, 2030, there will be indisputable scientific evidence for a technological artifact from an extraterrestrial civilization. The stakes might seem high, but the point is that we're now in a position where such evidence could realistically be obtained. Between the discovery of 3I/ATLAS, the launch of the Rubin Observatory, which will detect many more interstellar objects, and the construction of dedicated observatories by the Galileo project, we're entering an era where systematic searches for technological signatures are becoming possible. If artifacts exist, we'll find them. And if they don't, we'll gain invaluable knowledge about the natural diversity of interstellar objects, which is also profoundly important. But we have to be willing to look. We have to be willing to ask uncomfortable questions. We have to be willing to consider possibilities that challenge our preconceptions. The 1 in 100 million odds associated with 3I Atlas don't prove it's artificial, but they do prove that it's extraordinary, and extraordinary observations demand extraordinary attention. So where do we go from here? What happens over the next few weeks and months that will help us solve the mystery of 3I/ATLAS? The good news is that we're entering a prime observing period. As I mentioned earlier, three Ayat-Lashers moved far enough away from the Sun that Earth-based telescopes can now track it without interference from solar glare. And on December 19th, 2025, it will reach its closest approach to Earth at 269 million kilometers. That might sound far, and it is by everyday standards, but in astronomical terms, it's close enough to conduct detailed observations with our most powerful instruments. Telescopes around the world are already booking observation time. Research teams are preparing their instruments. The data that comes in over the next month could be decisive. Here's what scientists are looking for. First, spectroscopy. By analyzing the light passing through the jets, we can determine their chemical composition. If we see the signatures of water vapor, carbon dioxide, carbon monoxide, and organic compounds, that supports a natural comet explanation. Comets are essentially dirty snowballs, mixtures of ice and dust, so we'd expect to see these materials. But if the spectroscopy shows something unusual, ratios of elements that don't match typical cometary composition or compounds that are unexpected, that would be significant. It would suggest that 3 Ayat-Lace isn't a typical comet, even if it's still natural in origin. Second, velocity measurements. How fast is the material being ejected from 3I/ATLAS? Natural sublimation driven by solar heating produces outflow speeds of about 0.4 kilometers per second. If we're seeing speeds significantly higher than that, it would indicate a more energetic process. Chemical propulsion produces speeds of 3 to 5 kilometers per second. Ion drives can reach 10 to 50 kilometers per second. If the jets are moving faster than sublimation can explain, we need to understand why. Is there an internal heat source? Is there pressure buildup creating explosive outbursts? Or is something else generating the velocity? Third, trajectory analysis. This is perhaps the most important measurement. By tracking 3I/ATLAS's position with extreme precision over weeks and months, astronomers can detect even tiny deviations from a purely gravitational orbit. These non-gravitational accelerations are the smoking gun. For natural comets, we expect non-gravitational accelerations because ejected material creates a thrust, like a rocket exhaust. The comet gets pushed in the direction opposite to where material is being expelled. This is well understood and well documented in cometary science. But here's the key question. Do the trajectory changes match what we'd expect from the observed outgassing, or is there a mismatch? If 3I/ATLAS accelerating in ways that can't be explained by the jets we're observing, that would be extraordinary. And if those accelerations seem to be altering the trajectory in specific ways, if they're correcting the orbit or changing the exit path from our solar system, that would be even more intriguing. Fourth, fragmentation searches. If 3I/ATLAS broke apart during perihelion, we should be able to detect separate fragments by now. They would be moving on slightly different trajectories, spreading apart over time. High-resolution imaging should reveal multiple nuclei if fragmentation occurred. If we don't see fragmentation, if the object appears to be a single intact body, despite the enormous stresses of perihelion and the massive outflows we've observed, that tells us something about its structural integrity. Natural comets are fragile. They break apart under stress. An object that survives what 3I/ATLAS has experienced would need to be unusually robust. Fifth, temporal analysis. How are the jets behaving over time? Are they fading as we'd expect from depleting volatile reserves? Are they maintaining constant intensity? Are they showing patterns that suggest controlled emission rather than passive outgassing? Natural sublimation should gradually decrease as surface ices are exhausted and as the object moves farther from the sun, receiving less solar heating. If the jets maintain intensity longer than expected, or if they shut off abruptly rather than gradually fading, those would be anomalies worth investigating. Now, beyond these immediate observations, there are longer-term opportunities to study 3I/ATLAS. In March 2026, NASA's Juno spacecraft will have its encounter with the object from a distance of 53 million kilometers. Juno has sensitive particle detectors that might pick up material from 3I Atlas if the jets are still active at that distance. Even if direct sampling isn't possible, Juno can gather data about the object's brightness, any remaining activity, and its trajectory. As 3I Atlas moves outward past Jupiter and beyond, there will be fewer opportunities for close observation. It will become fainter, harder to detect, gradually fading from view as it returns to the darkness of interstellar space. Eventually, it will be gone, disappearing back into the cosmic ocean from which it came. This creates a sense of urgency. We have a limited window to gather data about this remarkable visitor. Once it's gone forever. We'll never see it again. The opportunity to study an object from another star system up close is rare and precious. We can't afford to waste it, but here's something exciting to consider. 3. Atlas might not be the last interstellar visitor we study in such detail. The Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, is scheduled to begin operations soon. This facility will conduct the most comprehensive survey of the night sky ever attempted. The Rubin Observatory will detect many more interstellar objects we're currently missing because our surveys aren't sensitive enough or comprehensive enough. Some estimates suggest we might discover multiple interstellar objects every year once Rubin is fully operational. This means 3I/ATLAS, as fascinating as it is, might be just the beginning. We might learn that interstellar visitors are more common than we realized. We might discover a whole population of objects passing through our solar system, each with its own story to tell about the distant stellar systems where they originated. And here's where it gets really interesting. The more interstellar objects we detect and study, the better our statistics become. If most of them are clearly natural comets and asteroids showing typical characteristics and behaviors, then 3I Atlas becomes even more anomalous by comparison. It would stand out as genuinely unusual. But if we discover other objects showing similar anomalies, similar statistical improbabilities, similar behaviors that challenge natural explanations, then we start to see patterns. We start to build a data set that allows for more robust conclusions. The Galileo project, led by Professor Avi Loeb, is building dedicated observatories specifically designed to detect and characterize unusual objects in our skies. These aren't traditional astronomical telescopes. They're designed to capture high-resolution data on objects moving through our atmosphere or our near-space environment. The goal is to approach the question of extraterrestrial artifacts scientifically, not with assumptions or preconceptions, but with instruments and methods capable of gathering definitive data. If technological objects are visiting our solar system, whether from other civilizations or our own future missions that have returned, we should be able to detect and identify them. This represents a fundamental shift in how we think about the search for extraterrestrial intelligence. For decades, SETI has focused on radio signals, looking for messages from distant stars. But what if the first evidence isn't a message? What if it's a physical object we can observe, track, and potentially even approach? The technology needed to detect interstellar spacecraft isn't exotic. It's essentially the same technology we use to study comets, asteroids, and other solar system objects. We just need to apply it systematically and be willing to follow the evidence wherever it leads. Why does this matter? Why should we care about one object passing through our solar system? If 3I Atlasis natural, we're learning that interstellar comets are far more massive and active than predicted, expanding our understanding of the galaxy's material. That's valuable knowledge. It tells us something about how planetary systems form, how material is distributed through the galaxy, and what conditions exist in other stellar neighborhoods. But if it's artificial, that would be the most significant discovery in human history. It would prove we're not alone, that interstellar travel is possible, and that other civilizations exist or existed. The philosophical and scientific implications would be staggering, fundamentally changing how we see ourselves and our future. Even the possibility deserves serious investigation. Scientists like Avi Loeb are pushing for systematic searches, not because they're convinced, but because the question is important enough and the public is ready. Look at the interest in 3I/ATLAS. There's a hunger for knowledge about our place in the universe. We've covered extraordinary observations, massive jets extending millions of kilometers, 7 distinct outflows at perihelion, statistical probabilities of 1 in 100 million missing Mars data. These are legitimate scientific observations demanding explanation. Stay curious, stay informed. Don't dismiss possibilities just because they seem unlikely. The universe is vast and full of surprises. 3I Atlasis moving through our solar system right now. Every day brings new observations. This is science in action, and you're part of it. By learning about these observations and thinking critically, you're participating in humanity's quest to understand our place in the cosmos. The coming weeks are crucial. December 19th brings the closest approach to Earth. Spectroscopic data is being collected. Trajectory measurements will reveal non-gravitational accelerations. The high-rise images will eventually be released. Each piece brings us closer to understanding. The story is still being written. The most important chapters might be yet to come. Whatever we discover will teach us something profound about the universe. Thank you for joining this journey through one of the most intriguing discoveries of our time. Keep looking up. Keep asking questions. 3I Atlas might be showing us that the universe is even more interesting than we imagined.